Lab 5, Faraday's Law. Introduction. So the purpose of this lab is to explore Faraday's Law by observing the behavior of a magnet falling through a roll of aluminum foil and creating a computational model to explain our observations. Models and principles. The major physics principle employed in this lab is Faraday's Law, which states that the EMF in a closed path is equal to the negative time derivative of magnetic flux. In other words, the system will induce a current in order to counteract the change in magnetic field going through the system. This magnetic field can then act on the object that is providing an external magnetic field, in this case a magnet. And through this lab, we were able to observe Faraday's Law in action in the real world and also corroborate our observations with a computational model. We will be utilizing Faraday's Law, the idea that the EMF through a closed path is equal to the negative time derivative of magnetic flux going through the closed path. We will also be utilizing the equation for the magnetic field of a magnetic dipole and the equation for the magnetic force on a piece of wire caused by an external magnetic field. We are assuming that our magnet and our tube both function as magnetic dipoles. And for the experiment, the physical experiment component of this lab consisted of letting a bar magnet fall through a roll of aluminum foil and recording the time it took for the magnet to go through the roll. This was done 5 times in order to obtain an average time taken to traverse the tube, which ended up being 0.274 seconds. This wasn't much longer than the time it would take for the magnet to fall through free space, but it was definitely longer. The system in this experiment was the aluminum roll gaining current, and the surrounding contained the magnet, which provided an external magnetic field and was acted on by the magnetic field generated by the aluminum roll. After conducting the experiment, we created a program to model the magnet falling through the roll of aluminum foil. We first entered the dimensions of our tube and the mass and magnetic dipole moment of our magnet. And then we created functions to calculate the magnetic field by a magnetic dipole and the time derivative of magnetic flux. The time derivative of magnetic flux was calculated by integrating magnetic field with respect to area, which yielded the equation shown here. And our program contained a loop in order to simulate the magnet and its velocity and position continuously through time. And finally, we calculated the magnetic force on each ring by calculating current and plugging in values for current, length, and magnetic field. And in the end, this was our velocity versus time graph. Also, the time spent in the tube calculated by the model was 0.354 seconds. And when viewed from above, the blue ring here represents clockwise current and the red ring represents counterclockwise current. And we know this because of Faraday's Law, which states that current will be induced such that it counteracts the change in magnetic flux. Since we drop the magnet with its north pole facing down, the red ring represents an increasing magnetic flux as the magnet falls. Therefore, the red current must be counterclockwise by the right-hand rule in order to counteract the change in magnetic flux. A similar things happen in the blue zone, where there is an upward change in magnetic flux as the magnet falls. And when we flip the magnet falls through the roll in the same manner as before, increasing in speed as the magnet gets closer to the bottom. The red ring from before would now be clockwise instead of counterclockwise, and the blue ring would be counterclockwise. But the magnet would still experience an upward magnetic force due to the rings acting as magnetic dipoles. The computational model calculated a time of 0.354 seconds compared to our experimental result of 0.274 seconds. The computational model might be made more accurate if more calculations were added to account for any change in magnetic flux after the magnet falls out of the tube but still affects the tube. The shape of the graph shows that speed increased at a decreasing rate instead of at a constant rate, showing that there was a changing net force acting on the magnet, meaning that the upward acting magnetic force on the magnet must have been increasing. And for our discussion questions, the first one asks, what if the resistivity of the conductor were reduced to as close as possible to 0? And if this happened, the magnetic force acting on the magnet would be much stronger, resulting in the magnet reaching a constant speed very quickly, or maybe even stopping or going back up the tube. And then what if there were holes or slots cut into the tube? If this happened, there would be less ring currents, and therefore the magnetic force on the magnet would be weaker, and the weaker magnetic force would cause the magnet to fall faster. And in conclusion, to summarize, we designed an experiment to observe the idea of Faraday's law. Our observation that a bar magnet falls slower through a roll of aluminum foil than through free space was corroborated by a computational model, which led us create a mathematical model to explore the system and to verify our observations.